Good afternoon and good morning, depending on which coast you're joining us from. I want to thank you for joining Astrix Technology Group as part of our webcast series. Today's session is entitled Integrating Lab Data Automation and Scientific Informatics to Facilitate Data-Centric Research. This session is going to be presented today by Dotmatics. But again, I want to thank everybody for joining us for this, what is a series of webcasts presented by Astrix Technology Group. So before we get into the presentation materials from our speaker today, I want to give everybody a quick summary of who Astrix is, what we do, and why we're hosting this series. This is a series that's running well up through February and into March. We are a company that provides informatics professional services and staffing, and we're dedicated to serving the scientific community. The company was established in 1995, is privately held. It originated as the IT division of a company called APBI, which was a $300 million life science research organization. Today, we operate from 7 offices in the United States and beautiful Costa Rica, and we have our headquarters in Red Bank, New Jersey. The customers that we service are Fortune 1000 life science enterprises, chemical, CPG, government, research institutions, companies with large and fast-growing IT, where they have some very specific needs around compliance and outsourced services. Our mission is and always has been to deliver scalable, sustainable solutions for the scientific community. In terms of the professional services work that we do, when we look at this from the lens of scientific data systems, Astrix Technology Group has an entire suite of solutions that we bring to bear. First, on the front end of it, it's really business process analysis and enterprise architecture. These are really kind of the two services that help laboratories figure out what is the right mix of solutions and how they should be deployed, whether they're on-prem or in the cloud, and how they're distributed, and basically what does the right stack look like. Then we get into technology selection services, where we can go out and select and evaluate different vendors that we believe is going to suit the needs of your individual organization. And then we can do development and implementation, and then finally computer systems validation on the back end. There's also hosting and management services of these applications, and finally the ability to staff professionals on both the IT and the scientific side to not only run these systems but also staff your lab. And then at the end of the day, we evaluate, implement, and manage systems to enhance the collection and processing of scientific data. Okay. So with that, we're going to take a moment and introduce our speaker for today. Rob Brown is the VP of Product Management and Product Marketing at Dotmatics. He joined Dotmatics in 2015, having previously spent about 10 years at a company called Accelerus. There he was responsible for the product marketing teams for cheminformatics and bioinformatics for the life science industries. And prior to its acquisition by Accelerus, Rob was a director of product marketing for a company called Pipeline Pilot, and I hope I'm pronouncing this right, Cytigic. And he also held positions at MSI and Abbott Labs, and he received his PhD in cheminformatics from the University of Sheffield in the United Kingdom under the direction of Professor Peter Willett. So we're thrilled to have Rob with us today. I'm going to just go ahead and take a moment here and get him queued up. So bear with me one sec, and we will be right on. Folks, if you could verify if you're hearing me right now, if you're hearing the audio, I know we had a couple of audio issues here, so we're trying to get those rectified real quick. If you can just verify that you're hearing me right now, that'd be great. All right, if you're hearing me right now, that would be good. I want to go ahead and do another quick test and of the video, make sure if you're hearing that. So bear with me here one sec. And we'll go ahead and get it. Appreciate your patience here. All right.
Good morning, good afternoon, everyone. I'd like to start by thanking Astrix for organizing the webinar and giving us the opportunity to...
All right, we'll do a quick pause there, folks. Was that audio coming through better? If you could please use the chat function. Okay, thank you very much. Appreciate it. Thank you for your patience.
So here's the outline for today's talk. I'll start with some background on the need for data automation as an integral part of data-centric research, and then I'll walk through a set of examples. So first, on the automation of lab data processing alone, we use the example of a mass spec call facility. Next, I'll talk about the process of automating lab data into experiment capture, using an example from assay analysis. Then we'll look at the value of data for scientists, using an example of voice control of the ELN. And then finally, automation all the way from data acquisition to learning, using an example from bioreactor monitoring. So as many of you on the call today will be fully aware, the research process has been changing in recent years, from being very process-driven to being much more data-driven. So we have a variety of decisions being made on ever-increasing volumes of data available from a wide variety of sources. But one of the biggest challenges with data-centric research is that there's still a lot of manual data processing taking place, and that generally is not a good thing. It's slow, so it impacts the efficiency of research, whether that's internal or with partners, and at the same time it impacts the quality, meaning that critical scientific decisions might well be being made on error-prone or dirty data. And just to put a few statistics around this, so firstly on the efficiency, it's been estimated that a typical scientist could spend up to 90 minutes a week on one-day data processing. And in extreme cases, such as an analytical lab that we'll look at in one of the first examples, it could be up to 80% of their time. Things aren't much better with collaborators. One data point from a bio-IT symposium a couple of years ago was from a company that was having to spend half an FTE internally for every CRO FTE just to process the data that was coming in. And in terms of efficiency, manual data transfer was introducing a lag time of up to 7 days. And that's from producing a result at a CRO to it being available to use back at the sponsor company. And then in terms of decision support, one example is from a recent report that suggested 50% of movement experiments in pharma process, 25% of those were attributed to the integrity of the data being used to build the models. So clearly, if we could improve both the efficiency and the integrity of data processing, that's going to be a great help to that situation. And to do that, we can turn to data automation. So let's start with just the instrument data. Imagine, as it shows on the screen, that we had a fully automated data pipeline, that we could feed instrument data into one end, turn on the tap, and out the other end would come fully formed decisions. Obviously, this is somewhat wishful thinking at this point, but we can at least break it down into steps so that we can start making progress. So what would we need to do? Well, first we'll need to automate the acquisition of that data from the instruments. Given that that's often in files with proprietary unstructured formats, we then need to parse out that data and metadata, validate it, and transform it into a standard format. Then we need the creation of experiments, upload the instrument data into those experiments, and then automate the necessary analysis to obtain a result. Next, we'd want to automate joining that result with all of the other project data that we need to consider, and ideally feed all that into some kind of automated learning. So then, we would be ready to start making our decisions, and those would be made in a much more efficient manner on clean data. And of course, it's not just instruments. As I said on the previous slide, a lot of that data is coming in from CROs. And even when scientists are generating data in the lab, as you'll see later in this talk, there are opportunities to automate their data capture process. And the other important dimension to all of this is that all the way through this process, the data should be persisted, actions on the data should be audited, and the data should be secured end to end. To achieve all those goals, we need to start thinking about how can we build out this process. And to start with, it's important that the process is built on the platform. Well, why is that? Well, the platform brings you a couple of things. Firstly, it gives you the ability to have an efficient, seamless workflow as data moves from one step to the other, making sure there's no need for human intervention. And that's also how our data security and data integrity are going to be assured. But you notice on this slide it says platforms, and the platform, for once, that's not just a typo on my part. The reason for that is that the challenges of data automation are fundamentally different than those of experiment capture and analysis. And so there really needs to be a separation of concerns. This is not an original thought of mine or of Dotmatics. This is based on a broader scheme published by Mike Chandler last year. For those of you with a Gartner subscription, the full report reference from Mike is shown at the bottom. But the report does make it clear that there still needs to be very tight integration between the platforms to support the end-to-end processing I've already discussed. For those who are not familiar with Dotmatics, we sit squarely in that red box on the right-hand side. We are an example of a scientific informatics platform to capture experiments, join and find project data, and then analyze the data to make decisions. So from our point of view, what's the reality in many organizations today? The right-hand side of that workflow, we feel, is pretty well integrated with a nice flow from experiments to project data to analysis. The gap that we primarily see is between the data coming in from the instruments or CROs and then getting that data into the ELM or the assay data management system to kick off the rest of the process. So for instruments, many times that's a manual data gathering process. Worst cases, scientists are collecting files around the lab with USB sticks. Slightly better, they are at least browsing networks to instrument PCs to find the data, but then they're still having to manually process and upload it. And in terms of data exchange with CROs, things are becoming more automated, but still it's often a process that involves email or SharePoint, using those to exchange Excel spreadsheets or PDF reports or PowerPoints. And as I said, that all comes to issues around data integrity as well as turnaround. So the first example I want to show you is just going to focus on how we replace that piece on the left-hand side with automation. So specifically, that's automating data acquisition, persistence, parsing, and display of data. From the diagram I just showed you, that was the missing link for Dotmatics. A couple of months ago, we announced the acquisition of a Boston-based company called bioreactor. The whole reason for that acquisition is that they are the solution to that missing link, providing the lab data automation platform needed to fill the gap. The solution starts with an application called Darwin Sync. This has a client that's installed locally on PCs connected to instruments and performs file sweeps to gather up new and modified instrument output files. It can equally be used to gather up files from scientists and CROs. But in any case, those files are then encrypted, uploaded to the Darwin Sync cloud application, where the files are stored in a secure data vault implemented as a data lake. Parsers are then used to extract the data and metadata from those proprietary files into standard formats, and then processes can be defined to QC the data. The application has many parsers already available if they're standard instrument formats, and bioreactor has an advanced meta-language capability that allows them to rapidly develop parsers for previously unseen types. So when bioreactor is used alone, this data is then presented in dashboards and lightweight cloud apps to provide operational insights into the data. It can also be handed off over APIs, as we'll see in a subsequent example. So the other important point about this is the scalability, with the ability to connect thousands of instruments, hundreds of users, and manage tens of terabytes of files, which is critical for the kinds of high-throughput experimentation we're seeing today. So here's our first case study from a large pharma customer of bioreactor that demonstrates the dramatic increases in efficiency that data automation can bring. The example relates to the collection and monitoring of mass spec data in a core facility. The company was generating between 20 and 100 gig of data a week, and they had a legacy on-premise solution to store and analyze the data. And it was then taking every scientist in that team 1 whole day a week just to gather up and load their data into the solution, and then a further 1 to 2 days to analyze the data. So you can see how quickly we get to that 60 or 80% of a scientist's time I talked about earlier. So that's obviously inefficient, it requires a lot of human intervention. And the volume of data was overwhelming, processing was slow, so it was hard to quickly gain any operational insights. So for example, instrument drift was hard to track as it was happening, meaning that runs were lost and had to be repeated. So Darwin Sync was implemented to gather up the data, sync it into the data store, automatically QA it, and then visualize the results in a variety of ways. And just one view is shown at the bottom of the slide, but there are a whole set of outputs to explain what was happening with the runs. So the nice thing about this is the customer then went back and analyzed the impact of this change. So with the solution in place, data collection was sped up by a factor of 63 times. There was also a backup of the data problem that was automated and became 50 times cheaper than with the previous solution. But here's the critical statistic. Each scientist saved 1 to 2 days a week. So that whole day of data sync was gone, as well as at least one of the days of the mundane data processing tasks. And that frees up the scientists and helps them keep up with the lab throughput. There's also an additional benefit, not just from speeding up the process, but applying the automated data QC, because that allows drift to be spotted in time to do something about it. So that's the first example. Moving on to the next one, this takes things one step further and looks at the value of adding in automation of experiment capture and analysis. The process is going to start just as before, so from left to right, files come off instruments, gathered up by Darwin Sync, uploaded to the lake, files are then parsed and the data and metadata extracted. The difference this time now is that the data is going to be converted into standard format and then handed off over an API to be consumed, in this case in Dotmatics, by Studies, which is the Assay Data Management System, or Studies Notebook, which is the ELN. But with the API, of course, this could also be sent to any other third-party software. For this example, I chose assay analysis. So let's start with a look at assay analysis the hard way, by which I mean the traditional manual process. So it starts with the instruments, which in this case will be plate readers, generating files on their connected PCs. The scientist is then going to gather those up, either over the network or by USB stick. So next, the scientist is going to start the assay data management software and create a new experiment. And assuming the file formats are understood, they'll then use a wizard to upload all those files, define the plate formats, identify the samples, and get the data loaded, which gets them to the top right of this slide. Then as we move towards the bottom right, they're going to go through manual data analysis, calculating and validating curve fits, assigning curve classifications. And only then, on the bottom left of the slide, is the scientist ready to make determinations about the results and, if appropriate, publish those to the project. So in low throughput labs, this is not ideal, but it's okay. But the more you think about high throughput labs and the number of experiments that can be done versus the number of scientists typically available in these labs, you can see that it rapidly becomes unsustainable to do this the manual way. So let's add in data automation. Now the files from the instruments are collected, Darwin Sync, put in the lake, stored and parsed. As I said before, the standard objects are sent over API to the assay data management system. But the API is going to do more than just send the data, however. It is actually going to automatically trigger the creation of a new experiment. It's then going to trigger the loading of the data and the samples. And then within the assay data management system, that in turn is going to automatically trigger initial curve fitting and initial curve classifications. So that's happening then all without scientist intervention and therefore without any chance of operator error. The scientist comes into the process only when the results are ready to review, to validate, and to publish. And this makes them much more efficient and be able to process many more experiments per scientist. So seeing is believing, so let's have a look at a quick working example in a video. Top left, we see a PC connected to our plate reader. Bottom left, I'm logged into the BioReactor cloud, and on the right, I'm logged into the Dotmatics Studies application. In BioReactor, I'm showing a view of all connected instruments and uploaded files. I'll start by searching for files only from the instrument connected to the PC above. Now imagine the plate reader has output a new file into the monitored directory. If I go back and refresh my BioReactor view, I see the file in the repository. Behind the scenes, BioBright is now parsing that file for the screening results, samples, and cell lines, and then calling the Dotmatics API to create a new experiment with the data. So if I now go to Studies and refresh the list of experiments, I see that a new experiment has been created. When I open that experiment, you can see that 6 plates of data have been loaded. The curve fits have been calculated and are awaiting validation, and that initial curve classifications have also been assigned. So without any human intervention, we've gone from a plate being read to an experiment being ready for final analysis, sign-off, and publishing. Okay, so that was automation into experiment example from an instrument, but now here's an example where we can actually improve the data handling when the data is coming from scientists themselves. And to be clear, this is scientists who are already equipped with an ELN. So for this example, we've worked with our partner LabVoice, and if you're not familiar with them, it'll be very clear what they do very shortly. But here's the challenge, which is that scientists often don't have direct access to the ELN while they're in the lab. Maybe because the space constraints precluding lab computers, or just because it's impractical to interact with an ELN when you're wearing the necessary protective equipment. So how do scientists deal with this? Well, they use paper. This is nicely illustrated with the example on the right here for a simple material weighing. So the scientists are starting off in the office, they create an ELN experiment, and then enter the material and expected weights. Then they memorize that, or write it all down on a piece of paper, and go into the lab. In the lab, the piece of paper tells them what they need to weigh out, and then, of course, they write the actual weight and associated data on the same piece of paper or on the back of their glove. Finally, and this should probably be shown as back in the office on that diagram, then they transcribe all that data into the ELN. So that's inefficient, and you can definitely see the opportunities for transcription errors all the way along the path there. So how can we make this better? And that's where LabVoice comes in. So you may have guessed, since the clue's in the name, LabVoice are a voice automation company. And we've worked with them to pair their technology with the ELN. So as with all the examples in this talk, the aim is to both improve the efficiency of data capturing and to ensure it's captured in such a way that it guarantees its integrity. So how would this work in the case of that material weighing example? Well, we start exactly as before. The scientist in the office creates experiment, enters material, and expected weights. But now they don't write anything down. They simply go off to the lab equipped with LabVoice on their phone with a headset or a dedicated hardware device. Now they ask the ELN, first for the correct experiment and then for the amounts they need. And then as the amounts are weighed out, they either tell the ELN what those values are directly or even ask the equipment to send that info directly into the ELN. So everything's done quickly and there's not a piece of paper in sight. Again, seeing is believing, so let's have a look at a couple of examples, both of which are designed to demonstrate the two-way interaction between the ELN and LabVoice. The first one shows the material weighing scenario that I just talked about, so we'll first set up the ELN experiment in the office and then transfer it to a colleague with a request for weighing. The colleague will go into the lab equipped with their LabVoice-enabled device and complete the request, and then finally we'll go back to the ELN to see the updated amounts that have been entered.
In the office, the chemist creates a new experiment and adds a description. They sketch or paste the planned reaction. And define the desired quantity of the limiting reagent. In this example, once the experiment is set up, it is transferred to a colleague with a request for weighing. Later in the lab.
Hey, LabVoice. Continue my experiment.
You have a few open experiments. The most recent one is 139045. Do you want to continue it?
Yes.
What would you like to do?
Weigh reagents.
Hang on while I get the reagent list. Scan your first reagent. You need to weigh out 100 milligrams of benzohydrazide. How much did you weigh?
100.5 milligrams.
Scan the next reagent. You need to weigh out 77.943 milligrams of benzaldehyde. How much did you weigh?
78 milligrams.
You're done weighing all the reagents. I've updated your experiment. Back in the office, the reagent table has been updated.
The second example shows more free-form data entry. Again, we'll first start in the office setting up a new experiment, but this time in the lab via lab voice, we then add data to that experiment. Specifically, we'll create samples, upload an image, and create a text note. So here's the notebook with the new experiment.
Hey, lab voice. What are my experiments?
Your most recent experiment is 139,012. Would you like to continue this one?
No.
Okay. Which one?
Experiment 2.
What would you like to do?
Scan samples.
More?
Yes.
More?
No.
Your samples have been added. Would you like to do anything else?
Take a photo.
One moment while I upload that photo for you. Your photo has been added to your experiment. Would you like to do anything else?
Add an observation.
What's your observation?
The samples are clear and free of particulates. Stop.
1 second. Your observation has been added to your experiment. Would you like to do anything else?
No.
Okay. I've sent you a link to your experiment.
So now we go back to the office, we reopen that experiment. There are samples with the barcodes, and on the next tab you'll see in a minute the photo and the voice note, or the note from the voice transcription. So now onto the final example, and that's really taking the process from end to end. So now we're going to go from automated data acquisition all the way to the application of learned models and prompting directly decision making. The example here comes from bioprocessing, specifically monitoring bioreactors. And again, it comes from a large pharma customer of BioBrights. So they have a legacy process shown in this diagram. So the scientist prepares cultures, sets up the reactor, initiates the run, and then the reactor produces a whole set of sensor data, which is that raw data shown in the diagram in the middle. The scientist then has to gather that up and manually inputs it into an Excel spreadsheet. They then use Excel for the analysis, and that spreadsheet becomes the basis for a set of discussions and decisions about the run. Now, the problem with that piece on the right there is that whole process could well take a couple of days to complete. So why is this a problem? Well, apart from just the efficiency and use of scientists' time, the problem is that bioreactors can suffer from crashes, specifically dissolved oxygen crashes. And those have a number of bad consequences. You can have higher cell death, you can get lower yields, you can have higher impurities in your product. And the worst case is you lose the entire high-value content of your reactor. So to sum up the situation, the legacy process was manual for both data gathering and data analysis. Data collection is slow, so therefore necessarily decision-making is slow. It's potentially very costly if you lose a run or the entire contents of the reactor to a crash. And the fundamental problem is that those crashes were not predictable. With the speed of data processing, it simply wasn't possible to anticipate a crash and do something about it. So how do we make this better? Well, in this case, we implement BioBright to do two things. We implement BioBright to gather up all of that sensor data automatically as it comes off the reactor and get it into the lake ready for analysis. But the second thing that BioBright does then is apply a machine learning model to that data in real time to predict the likelihood that a crash is going to happen. And that model within the system has been trained using sensor data from previous successful and unsuccessful runs. So the variables in the model are the sensor data items such as O2 and CO2 flow rates, agitation, etc. So what does that look like? Well, this chart shows you what a run looks like when a crash does happen. On the chart, you see time on the x-axis, so this is over about an 8-hour period. And on the y-axis, you see the sensor data measuring the dissolved oxygen. So blue is in a healthy range and red is not. And you can see that the run is going well until all of a sudden an event happens around 1:15 a.m. and then the reactor crashes very quickly. Now if we look at the model output, and that's what we see in the chart at the top there. So time again on the x-axis. On the y-axis, you see the likelihood that a crash is going to happen. So 0 is fine, it isn't going to crash. 1 is it's definitely going to crash, and it's going to do it soon. So something around 0.5 is an interesting value to start monitoring, because that means it's more likely going to crash than not. So it's time to take some action. So for this run, you can see that from 7 to 9:30, everything's fine, and then it begins to fluctuate a bit, but the situation stabilizes. Then everything's okay till around 11:15. By 11:30, it's really clear that something bad's going to happen. And if you let this run, as was this case, by 1 a.m. it's certain it's going to crash, and then at 1:15 it does. The point of this is if the operator was given an alert between, let's say, 11:30 and midnight, while they might not be thrilled given the time of day, it does give them fair warning to go do something, to adjust the agitation or the flow rates, or worst case, shut it all down and salvage the reactor contents before they're all lost. So with the BioBright solution, everything's automated, all the way from the data collection to the data analysis to the application of that predictive ML model. The outcome, dissolved oxygen crashes become predictable up to 2 hours ahead of occurrence, so runs can be saved or the biomass salvaged, because critical decisions can now be made fast enough to influence the outcome. So just to summarize, because that's quite a lot of examples in quite a short time, but hopefully what you've seen here is that the application of data automation can add value at every step in that process that I outlined at the beginning of the talk. And thinking back to the big challenge that I started with as we move towards high-volume data-centric research, we need to make sure that process efficiency and data integrity don't suffer because data handling and data processing are not optimized. To do that, we need to ensure that data processing is automated wherever possible. And despite all the exciting technology I talked about, what's the most fundamental thing we've done here? What we've actually done is freed up highly experienced, valuable scientists from mundane data processing. So now they can go focus on analysis and decision making, and they'll have the best, cleanest data to do that. So with that, a number of people I need to thank here. Charles, the CEO, Brian, the COO. Nate is one of their senior architects who worked with Aaron from Dotmatics, the application science team, to build out the assay demo I showed you. And then from the lab voice example, Fred is their CEO. Dan put together that second video, and whose dulcet tones you heard talking to lab voice. And Toby worked with Aaron to build out the example, which was then executed in that video. And with that, thank you very much for your attention.
Great, thank you, obviously, to the team at Dotmatics for putting a wonderful presentation together. I really liked the way you incorporated the demo and using the different technologies. That was pretty sharp, so thank you for that. And I obviously want to thank everybody for your patience through some of the audio issues. It's always a little bit of a challenge when we're dealing with multimedia, so I thank you for that. We were able to hopefully get that thing straightened out in not too much time, and kind of get us back on the right track. So with that, a couple of things. We'll go ahead and get this recording stopped.